Alright, grade 12s. Let's look at question 2 of the June control test, term 2. So, they tell us that a diagram below shows a child with a mass of 20 kilograms. Okay, there we go. Sliding from rest. So, over here, my initial velocity is 20 meters per second. Slides down a frictionless ramp to B, then slides over a rough section. So from B to C there's friction. There's no friction from A to B, and the vertical height is 5.1 meters. Then they say use energy principles to calculate the speed of the child at point B. Energy principles mean conservation of mechanical energy, net work done by non-conservative forces. You cannot use equations of motion. It's not linear motion. What we expected that you would have done, because this is actually the easiest way to do it, so if you look at 2.1, energy principles usually means that we use mechanical energy at point A is equal to mechanical energy at point B. So we know the EK at point A plus the EP at point A would be equal to the EK at B plus the EP at B. Alright, so a half MVA squared plus, I was about to do EK again, plus MGHA is equal to a half MVB squared plus MGHB. Now at A it wasn't moving, so that's 0. At A, the child was what, 20 kilograms? Oopsie. 20 kilograms, it's 9.8. It's 5.1 meters above the ground. We wanted to know how fast the child was going when they got to B, and EP is 0. Now it's just solving for V, okay? And V is 10 meters per second, doing it this way. Now what you could have done, and I did see this quite often, is you can use work done by the non-conservative force, because you recognized that the non-conservative force was 0, there was none, okay? So, work done by the non-conservative force is changing EK plus changing EP. That is 0. You can't leave that out, okay? You got to put it in there. So changing EK is a half MVB squared minus, and it's a half MV at A squared plus MGH at B minus MGH at A. Okay, so we have 0 equal to a half times 20 times VB squared minus 0 plus 0 minus 20 times 9.8 times 5.1. Now, if you don't get the final minus initial correct on this part, you're going to end up trying to find the square root of a negative number. You can't do that. Okay, you can't do that. It's mathematically not possible. And again, we're going to get, well, here you get 9.998, which rounds off to 10. Okay. The third option was to use W net. Here what you had to recognize is that because we were looking at something that was going down and we were looking at the non-conservative force, there was no non-conservative force. That means it's the conservative force of gravity that was doing the work. So net work was the work done by gravity, and gravity acts vertically down. We know what that vertical height was. So that means I could go FG delta X cos theta equal to a half MVF squared, well, they would have been at B, sorry, a half MVA at B squared. So FG is 20 times 9.8, delta X was 5.1, and this becomes cos 0 because it's moving down and gravity acts down. So we have a half times 20 times VB squared minus 0, and again you get 9.998, which is essentially 10. Alright, this isn't a great way to do it because we don't have friction, but it's perfectly acceptable. It's energy principles. Alright. Question 2.2, definition. That was pretty much quite important, and I'm not going to write these out, but definition for a non-conservative force: it is a force for which work done in moving an object between 2 points depends on the path. A lot of you just said it's a force that depends on the path or is independent of the path. It's not that. It's a force for which the work done in moving an object. Guys, you've got to learn definitions. Then they tell you the coefficient of friction between B and C. So mu K is 0,2. And first thing they say, state the work energy theorem in words. Well, that says to us that the net or total work done on an object is equal to the change in the object's kinetic energy. Once again, this was all or nothing, and it's net work done on an object, not by an object. Then 2.4, use energy principles to calculate the distance x. At this point, when you look at it, I just asked you the work energy theorem. We were trying to lead you to use the work energy theorem again, okay? Some of you tried to use other things, and I'll look at the other option, but actually I don't really want to look at the other option. We're just going to look at two options, okay? So, when we look at this, we want to use the work energy theorem, okay? So, W net equals changing EK. I need to recognize that the force that's acting on the object is friction. My net force can only be friction. There's no other force acting on my object to move it horizontally. So that means this is actually going to be friction, delta x cos theta equal to a half mv, and it's at C, but I'll final, minus a half mvi. Vi is 10. We've worked it out. Okay? We are looking for delta x. What I need is friction. I don't have friction. So now we need to remember, because we've done this before, that friction is mu k Fn. It's moving horizontally, so Fn is actually Fg. So to get friction, I'm going to have to go mu k times mass times gravity. Now, you can work out friction separately, or you can just substitute it into the equation, which of course is where we need to go from here. So I could go, this is now becomes my substitution. We just said it's going to be 0,2 times 20 times 9,8. That's FF. Delta x, friction, works in the opposite direction, so it's cos 180. A lot of you gave me cos 0. My final velocity is 0. Then it's a half times 20 times 10 squared. Now it's solving for delta x. At this point, because a lot of you gave me cos theta, you ended up with a negative distance. Guys, you can't. The distance is positive. It wasn't going backwards. It was going forwards. Alright? And delta x works out to be 25,5 meters. Now, you could have used work done by the non-conservative force, which is then changing EK plus changing EP. Essentially, the difference is this. You would still work out work done by the non-conservative force like W net, but you need to remember that changing EP equals 0. So you're doing a little bit of extra work to get to the same answer. Okay, be careful. Look at the question. I asked the work energy theorem. I probably want you to use it. Then, the demolition ball is used by a crane. is used by a crane to break the wall of a building. The demolition ball of mass 1,250 kilograms is lifted by the crane to a point R. Now, guys, here I needed you to recognize that this is a pendulum. It's going to go in a circular motion. The wrecking ball was not lifted vertically, it was lifted at an angle. First thing I asked for was for you to define the term power in words. Well, power is the rate at which work is done. That wasn't an issue. The issue is this. Calculate the average power dissipated by the crane in lifting the demolition ball to point R. A lot of you went, average power must be V if V average. Okay? This is the problem with this. We don't have an average velocity. This is circular motion. The velocity is constantly changing because its direction is constantly changing. I also did not say to you that I pull it up at a constant velocity. So this was an assumption. Those of you that did it, with the way you did it, you got a value for V, which actually ended up giving you the right answer for power, but your calculation, your physics is incorrect. We wanted you to use work. Power is work done over delta T. Recognizing that the work we're looking at here is the work done overcoming gravity because we're ignoring friction. So this actually has to be Fg delta x cos theta over delta T. Now possibly putting Fg there is not a good idea. What we had to recognize was that the force we have to apply must be equal to Fg. Some of you got a negative answer for power. Power cannot be negative. Power is a scalar. Alright? Power is a scalar. The force that's being applied is pulling it upwards. So that's why we're going to use Fg. So this is going to become 1,250 times 9,8 times 5,8 times cos theta over, and they said it took 60 seconds, which gives me 1184,17 watts. Please be careful with these ones. You can only use this equation when you have linear motion. So it's moving vertically upwards, completely vertically upwards, or it's moving horizontally, not for a pendulum. Be very, very careful.